review what went on in the first semester. I'm going to make several videos like this. I'll probably put one per day out each day this week and into next week so that we can cover this material again properly. In the first semester, everything we did basically was based on Newton's laws of motion, especially the first law. If an object is observed to be moving in a straight line with constant speed by one inertial observer, then they are going to be observed that way for all inertial observers. That means that the formulas that relate the coordinates of the two systems have to be linear, otherwise the straight line nature of the path won't be preserved. The standard situation that we studied was that the origin of both coordinate systems, or frames of reference, were located at the same place initially, both in terms of space and time, that the O bar was going to move to the right with speed v relative to O, and the simplest kind of situation you can have is given by the Galilean boost. All seemed well until it was found that the speed of light in a vacuum, as measured by an inertial observer, is constant. That's inconsistent with the Galilean boost, so this tells us the Galilean boost can't be altogether right. We drew some diagrams that included both space axes and also the time axis for both of the inertial observers. We had to think a whole bunch about this, but in the end, we found that the simplest transformation that is linear, that involves t, x, y, and z, but does preserve the speed of light, is this. This is a Lorentz boost in the positive x direction. If the speed is small compared to the speed of light, the latter three equations basically reduce down into the Galilean boost. The new thing is the time dependence. We generally adopt units so that the speed of light is 1, so that simplifies these formulas somewhat. If you want to explicitly write out the formulas, including all the terms that happen to be 0, you get these 4 equations. These 4 equations are abbreviated by this vector equation. This says mu bar could be 0, 1, 2, or 3, so for each one of the values of mu bar, x mu bar is going to be a sum over some kind of coefficients times the x coordinates. Lambda mu bar alpha is the partial derivative of x mu bar with respect to x alpha. It's the coefficient in the linear equation that gives you x mu bar that goes with variable x alpha. So in general, when we write out a linear transformation like this, we'll have 4 equations, each one of which has 4 terms, and these lambdas are partial derivatives of the new coordinates with respect to the old coordinates. Of course, you could write the inverse transformation also. X beta is some combination of the barred x coordinates. X beta will be lambda beta gamma bar x gamma bar. Because of the chain rule for functions of several variables, and using the Einstein summation convention on index alpha, we see the matrix of these numbers and the matrix of those numbers. When you do matrix multiplication, you get a matrix that's 1 on the diagonal and 0 every place else, just as it should be. Let L be the matrix of lambda mu bar alpha. L inverse is the matrix of lambda alpha nu bar. This says that L times L inverse is the identity, or L times the identity matrix times L inverse is the identity matrix. These are what are called, in ordinary linear algebra, orthogonal transformations. Physically, they represent rotations and reflections, and these leave the usual Euclidean distance invariant. If O measures the distance between 2 points to be 7, so will O bar. When we looked at special relativity, we found out that those kind of transformations don't leave the speed of light constant, so we had to figure out what was going to be left constant. We cooked up a quantity called the space-time interval, which we write as delta S2. Resist calling it delta S squared because it might be negative. It is the Euclidean distance minus the square of the difference in time. So in terms of matrix form, ordinary linear algebra orthogonal transformations, this kind of thing. Instead of that, we get this kind of thing. The 4x4 matrix in the middle is called eta. If you transform it from one coordinate system to another, you want to leave this quantity invariant. After much work, but basically similar to the ordinary orthogonal case, for a linear transformation with constant coefficients to leave delta S2 invariant, it is necessary that the transformation matrix times eta times the inverse of the transformation matrix must equal eta. This is a more general Lorentz transformation than just a Lorentz boost. Because I'm going to make a whole bunch of these videos, which I'm doing mainly because my voice keeps giving out on me, I'm going to stop there. Tomorrow we'll have another video where we begin talking about vectors in terms of four-dimensional space-time, and we will remind ourselves of many of these facts that we figured out in the first semester. I hope everyone's doing well. Stay safe.